Okay, guys, today's going to have quite a bit of a different feel. We're going to go through the counting principles today, or start them anyway, because a lot of probabilities for certain kinds of things can be found by counting things. Counting how many ways the event A can happen for the numerator, and counting how many ways the sample space can happen. Okay, so here's a quick example. Even though we don't have probabilities to go with them, sometimes you can draw a tree diagram to describe the possible outcomes for the following series of events. My boy Paul can take a bus to school or drive to school or get a ride from a friend. Okay, wait, he has no friends. It's just the bus or driving. Okay, clearly I was hilarious when I wrote this. You got to really want to see it, though. So he could take a bus or he could drive. For first period, he could be early or late or right on time. There's three options. Now, whether he's early, on time, or late, his first period teacher could either care or not care that he's present. Okay, so here's how the tree diagram looks like, all right? I'm going to try and put these like in the middle of this space. He could take the bus or he can drive. Those are the two ways my man Paul can get there. So now I'm going to go that there's three different things that can happen as a result of his different ways that he can go to school. And notice I'm trying to keep these aligned vertically, okay? Try and keep them aligned vertically. He could be late, he could be on time, or he could be early. That's probably not the order I should write those, but I'm going to stick with it. He could be late, he could be on time, or he could be early. Okay, and then once that happens, the teacher could care or don't care. And I'm going to abbreviate there because we're going to have to write these kind of small. Care or don't care. Care or don't care. Then down here, could care or don't care. Care or don't care. That's just screwed that up. I wrote care don't. That's okay. Care or don't care. And then at the bottom, care or don't care. Okay, kept them vertically. Okay, so I don't have probabilities that go with these, but I'm using that as a way to count how many different things I have. Like, for example, he could take the bus, be on time, and his teacher doesn't care. That's one way this could play out. Bus, late, and does care, that's another way this can play out. So the end results here are a quick way to count how many different options we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. N equals 12 possibilities. Okay? How many possible outcomes are there for this scenario? Okay, well, it's okay. Now, there are three, let's get the terminology right, different events going on here. The ride that he gets to school, timeliness, I don't know if I spelled that right, and care, whether or not the teacher would care. There are three different events, but there are 12 different possible outcomes. Make sure we have the terminology right. All right, I'm going to go to the second page. How many different ways were there for him to get a ride? 2. He could drive or ride the bus. How many ways are there for Paul to get to class time-wise? 3. Early, late, and on time. How many ways are there for the teacher to care about Paul, care or don't care? Okay. Those are the three different events that happen, and those are the amount of outcomes for each one. You can see them by how many things we have, right? There's 2 here, and then 3, 3, and then 2, 2, 2. So 2 and 3 and 2. 2 and 3 and 2. The multiplication principle says that if you want to count the number of possible outcomes, it's a really easy thing we're about to do here. When there are multiple events, you guys probably even know it, you can just multiply, instead of writing out that whole damn tree diagram, all of the numbers of outcomes for each event. What do I mean by that? For Paul, there should be 2 times 3 times 2, or 12 outcomes, which is the same as counting the ends of the tree diagram. Okay, the multiplication principle saves us some time. So now I'm going to ask you a couple questions about the multiplication principle. A license plate for a car in California always uses the following order. There is one letter at the beginning of the license plate. I might be making this up. I don't know. Then 3 digits, numbers 0 through 9, and then 3 letters at the end. How many different license plate numbers are possible? Well, if they have to go in that order, it's going to go 26 for that letter. There's 26 options, A through Z. Then 3 digits, there's 10 digits, right? So 10 times 10 times 10. I'm just using the multiplication principle here. Now here there were 3 different events. Here there are 1, 2, 3, 4, 5, 6, 7 events. So I'm going to multiply 7 numbers together. 27, 10, 10, 10, and then the last three are letters, so there's 3 more 26s. I would put all that in my calculator, and here's how many different license plates are possible for California. They got a lot of people out there in California, as evidenced by how many electoral votes they get in an election, right? Okay, so 456 million possible license plates. That number gets big in a hurry, and when you first start studying stuff like this, it seems like those numbers get too big, but it's legit. A phone number, excluding the area code, is a 7-digit number that cannot start with a 0 or a 1. It can start with anything else. How many phone numbers are possible for each area code? Well, if you can't start with a 0 or a 1, there's not 10 digits available for the first number in the phone number. There are 8 digits. And then for the other 6, there are 10 digits. So I'm going to put 10 sixes here and lose count and have to count 1, 2, 3, 4, 5, and then one more. So 8 numbers possible if you can't have a 0 or 1 to start, and then 10 for the rest gets you 8 million different cell phone numbers for each area code. I remember when I was a kid, cell phones weren't around, and so all of like Detroit and the lower eastern Michigan area was all the same area code, 313, and like New York was all 212. And then as more people got more phones and cell phones and stuff like that, there was tons more phone numbers needed. And so we have more area codes for each area now. The next part describes, isn't it fun when I tell stories about how old I am? Don't you guys enjoy that? I'm like a grandpa. The next part describes counting outcomes when sampling. Okay, this is important here. Listen to this. Sampling without replacement. Without replacement. Once picked, don't put them back. Okay? Once picked, don't put them back. Like if I roll a die and then I roll the die again, just because I got a 4 doesn't mean I can't get a 4 again. That's sampling with replacement. But if I'm shuffling cards and I give you one card and it's the Jack of Hearts, the next time I give you a card, it's not the same probability. That's sampling without replacement. Okay? A permutation. A permutation is a distinct arrangement of a group of individuals. Now, if you're arranging things like books on a bookshelf, once you put one up there, you don't have to think about where that one goes anymore. So this arrangement thing is you're doing something without replacement. Okay, that's how those two things belong on the same page here. All right. If I rearrange things like furniture in a living room, once I put a couch in a certain place, I'm not going to put it somewhere else. I'm rearranging things. So that's putting things or taking things without replacement. Let's go to the next page.